Now, materials are classified on the basis of how charge moves around in them. In conductors, charge is free to move. Actually, I shouldn't say charge. Electrons, I should say, are free to move, generally speaking. For example, many metals have a structure where the protons kind of cluster together in a sheet, and then the electrons aren't bound to a particular atom, so they're free to slide along the surface of the proton, of the surface of the metal. Metals are good conductors, especially copper is pretty good. It's often used. Copper is what's usually used in electric wiring because it is a good conductor and it's cheap. Silver is actually a really good conductor, but it's more expensive and it corrodes, so copper is used more frequently. Water conducts electricity, and therefore, because we're mostly made of water, people are pretty good conductors of electricity. If you've ever been out swimming when it starts to storm, you're told to get out of the water because water is a good conductor. If lightning strikes the water anywhere, charge will flow around and that won't be fun for you. So conductors are materials where electrons are free to move. So conductors are, like I said, they're used in electrical circuits and whatnot pretty often. The opposite of a conductor is an insulator, where electrons are not free to move. Examples of insulators are wood, rubber, there are other things. But you may have known this, if you're in a thunderstorm, your car is a safe place to be because you have your rubber tires that prevent you from getting electrocuted. Also, in walls, when they're wiring for lights and whatnot, usually the wires are coated in a rubbery sort of substance because they don't allow charge to flow freely. So those are a couple examples of insulators. Semiconductors can act as either insulators or conductors, depending on the circumstance. And what the circumstance is, it depends on the particular conductor. For some, it's the temperature that changes it. Some, it could be pressure, it could be any number of different things. There are different kinds of semiconductors where that they can act as either insulators or conductors depending on the circumstances. Silicon is a semiconductor, which is why it's used in computers, because then it can be manipulated to allow charge to flow or not flow, depending on what is required by whatever process the computer is doing. Another interesting example, there are some things called photoconductors, which allow charge to flow on the basis of whether or not there is light. So photoconductors are conductors when light is shining on them, but they are not conductors when they are in the dark. And this is actually how photocopiers work, like our our copiers out in the hallway. So there is a positively charged photoconducting material, and so then the areas the light hits, the charge flows away, and so then there's a negatively charged toner that then sticks to the dark areas that remain positively charged, and that's how you get your letters printed on a copy machine. That's pretty cool. Superconductors, they conduct perfectly freely we'll talk more about, there's a property of materials called resistance, which talks about how much they impede the flow of charge. Superconductors have zero resistance. So most materials, there is some kind of energy loss when power is coming through the power lines to come to your house or the school or whatever. There is some amount of energy that is lost. Superconductors conduct with zero energy loss. The problem is that superconducting materials generally only are able to do this at extremely low temperatures and or very high pressures. So the highest temperature at which they've gotten a superconductor to function, at least that I'm aware of, is around negative, what was it? I think it was like negative 65 degrees Celsius, which is pretty good because only like 10 years ago the warmest temperature they'd been able to do it at was like 3 or 4 degrees Kelvin, or 3 or 4 kelvins. Kelvin doesn't have degrees. Sorry about that. Yeah, but if you could get a superconductor to function at normal temperatures, that would be very helpful for transferring energy efficiently. There is also some cool stuff you can do. If you're interested, you can search magnetic levitation, and you can read up about that. That's something where in a superconductor you can keep a current flowing, keep charge flowing, and that allows a magnet to kind of levitate over the superconductor, which is a neat application. They have magnetic levitation trains, but it is expensive to keep the tracks cold enough for the superconductor to be a superconductor. Anyway, so there are a few different ways that objects can be charged. Triboelectric charging is one that we just already talked about, where you rubbing objects together. Charging with contact, conductors, because they allow electrons to flow freely, when two conductors are brought into contact, the charge kind of evenly distributes. So if one object is already charged, you touch it to a conductor and the charge will distribute evenly, and now that object is charged. So that's one way. Another way of charging objects. Induction is an interesting means of charging an object. So the way this works, you never actually touch anything. So you've got a conductor that is initially uncharged. So this is my conducting sphere, and it's connected to a ground. The reason it's called a ground is because the ground is an electrical ground. But what a ground is it's a place where electrons are free to flow in from or flow out from. The Earth's crust is a pretty good conductor, so any charge on the Earth's crust distributes itself evenly over the surface of the Earth. So a couple electrons being added to the surface of the Earth doesn't really change anything, because it's a very negligible charge over such a large area. So electrons are free to flow into the Earth or out of the Earth without having much of an effect. That's what a ground is. So we got this conductor, and initially, it's neutral. There's positive and negative charges hanging out all throughout. And then you take an object, and just for the heck of it, we'll say it's positively charged. It could be either. And you just bring it close. You don't touch the conductor. You just bring this object close. And when you bring it close, what happens? Well, we know like charges repel, and unlike charges attract. So now you've brought this close. Now what happens? Well, now your electrons all move over. Your electrons all move over close to this. The protons just kind of chill out where they were at, because protons aren't generally free to move. But the electrons have all clustered over here. Now, from your ground, the protons are over here, so the electrons in the ground are attracted, and they get kind of pulled in through the ground, and then that gives the sphere a net negative charge. Then you cut the ground. So you detach the conductor from the ground, and now there is a net negative charge. There's still, the protons are still there, but there is a net negative charge on this sphere that wasn't there before, even though we haven't actually touched it. So that's kind of interesting. The opposite effect happens if this object you're bringing close is negatively charged. Then electrons in the conductor would be repelled, would flow out of the ground, giving this conducting object a net positive charge. Then you cut the ground, it would be left with a net positive charge. It's just a little bit of introductory information about how charge works. And we'll talk more about it, and we'll do some demos in class, so I'll show you some of these effects and how they work, as well as get into quantitatively how electrical attraction and repulsion work. So this is your homework for next class. Yeah, and I'll see you then.